Hi everyone, and welcome to our video on what makes a function. So, a function is a set of ordered pairs where no x-coordinates are repeated. A rule will often define y as a function of x. So, in this example, it's asking, is y a function of x? If so, define the rule. Well, all I have to do is look at the x-coordinates, and notice there's no x-coordinate that is repeated here. So that means this is a function. Yes, y is a function of x. Okay, so that's it. So that's all we had to do. So there's no repeated x coordinates in this list. In this problem, they said to define the rule. Okay, so often they won't ask you to define the rule unless it's something that hopefully is clear enough. Well, notice what's happening between your x coordinates and y coordinates. This might look like a familiar notation. Here's where we want to think of the square. So 3 squared is 9, 5 squared is 25, 1 squared is 1, negative 2 squared is 4. Okay, so that's what's happening here. So if we square x, we get y. So y is x squared would be the defined rule. Again, let me just box those two like that. Okay, however, with functions, we often like to use this notation f of x equals y. So like with this one right above, we could have said f of x equals x squared instead. Okay, so that right there, that's how we say f of x. And it's just letting us know that we have a function in terms of x. So like over here, let me underline this one. So f of x means over here on the right will be an x expression. Okay, so that's just letting us know a different form to write these functions. Okay, and when it comes to functions, functions will have a domain and a range. A domain is all possible x values of a function, and the range is all possible y values of a function. Sometimes they'll list it as actual individual x coordinates and individual y coordinates, but most of the time we write these using interval notation. So they'll say interval notation written, let me put it like that, written in interval notation. And we'll break down what that means in our problem coming up. The first main function that we often deal with is a polynomial. While polynomials are nice, it's where a function's variables powers are all positive whole numbers. So that's what makes a polynomial. If they ever ask for the domain of a polynomial, our final answer will always be from negative infinity to positive infinity. Okay, so that means, what this means is that you can plug in any x value you want into your function and you will get a y value. So for instance, this wants us to find the domain of this function. Well, looking at those powers, those are positive whole numbers. So that means this is a polynomial. So f of x is a polynomial. And so what that means for our domain, let's do d with a colon for our domain, is that it's negative infinity to infinity. The other way that we might say this is all real numbers. Okay, so but that takes longer to write. It's quicker to do this parenthesis. So that's usually the way that we write these. Okay, so that's our domain for this problem. So again, all this means is I can plug in any x I want and it would give me a y coordinate. All right, so the next thing that I want to look at are graphs. So in this, it says find the domain and range of each graph. So if it helps, you can always put like, so it's in alphabetical order, domain to range, x to y. Okay, so domain range is alphabetical order, x, y is also alphabetical order. So that can help with making sure we're doing the right one. And then the second part is to use the vertical line test to see if a graph is a function. All right, so let's see. So let's do it in the order they want. So part A, find the domain and range. Okay, so the domain, the way that we look at it, so I want to look at it from left to right. Let me actually use purple here for the domain. So notice I'm gonna plot it kind of just below this graph. So let's do it below. So notice it starts with a solid dot, and it's kind of like as if this curve gets sandwiched from above and below to make a segment. So if I were to draw this left to right, I would be able to draw it as a flat surface until I get to 7, and at 7 I would have some open dot. Okay, and so this is a visual of the final answer for the domain. So we look at the x coordinates. So it's like I'm flattening this curve to be on the x-axis. So like it's squashed down from above and below. Okay, so like big old bricks are pushing it down or something. Okay, so it's hard to show on a computer like that with hands. Okay, so I'm thinking this gets sandwiched down into the x-axis, and well, it starts at x equals 0. Okay, let me get my pen. There we go. So x equals 0 is where it starts, and then 7 is where it ended. Okay, so these solid dots, let's put that information right here. So solid dots use brackets on the, oops, let's spell it right. Use brackets with interval notation. Okay, so that means we will start this at 0. Let me put my bracket down. So 0, and then, so this is telling us where it starts, and then including 0. And then we read it to the right, so it's going to end at 7. Open dots will get a parenthesis like that. Okay, so let's add that too. So an open dots use parentheses. Okay, and then the infinities always use parentheses. Okay, so from above we had negative infinity to infinity. Those are always using parentheses as the symbol. Okay, so that is the domain. Now, the next thing I want to do, so this is the smallest x-coordinate to the largest x-coordinate. That's what we can look at it as well if it is like a segment like this. So this is the smallest x-coordinate. That is the biggest x-coordinate. Okay, so our range, let's do that in green. So our range, okay, so I'm going to kind of do a similar thing where if I were to squash this graph so that it's squashed against the y-axis, so like some wall is closing in on it and squishing it down to be on the y-axis, then I would sketch this and say, well, right here, if there is no dot at all shown, it would automatically be a solid dot. So we would start this at -2, and then it squashes down until we get to 4. And then everything else is in between. Okay, so this open dot, that's okay that it's open. When it gets squashed onto this y-axis, this part of the graph would fill it in. Okay, so those are okay to have every now and then. All right, so this is it. So these are all of the y-coordinates as a representation using a vertical segment. So it starts at -2 and it goes to 4. So that means our range, and because there's solid dots at the end, it starts at -2 and goes to 4. Okay, or the other way, so in case you don't like the squashing thing that I'm kind of doing here, you could just think, well, looking at it from the bottom to the top is where you'd find your smallest y-coordinate. So that's at -2. So let me mark that. So this is the smallest y-coordinate. And then that 4 is the largest y-coordinate. And then all other y-coordinates are in between this curve. So there they all are. Okay, so the last part for this, part B. Okay, let me change it to blue. Okay, so part B. It says use the vertical line test to see if the graph is a function. The vertical line test is if you draw in any line. Okay, since I'm done with this problem, I'm just going to sketch in any line there. You could draw more than a single line just to really verify. But because any of the vertical lines that I draw, wherever I draw it, so it doesn't matter where I draw, it's going to pass at most one time through this curve. And that would mean that it is a function. So yes, this is a function. So all of these vertical lines pass through at most one time. If they pass through more than once, then that means it would not be a function. Okay, so that's all we have to do. It's a quick visual check. Okay, so for this next one, we have a circle. Now, that dot in the middle is just showing where the center is, so that's not really part of the graph. Okay, so that little dot there at -2, 2 is just showing where the center of the circle is. Okay, so that's not really part of the graph in this problem. All right, so anyway, we will still look at it to find our domain and range. Okay, so our domain, let me do this in purple again. Okay, so our domain, the domain, let's use it like the second way that we said, the smallest x coordinate to the biggest x coordinate. Well, my smallest x coordinate looks like it would be at -5 over there on the very far left of my circle. And then I have all x coordinates until I get to 1. Okay, so it looks like it'd be -5, 1. And they each get a bracket because there's no open dots. We assume that there are solid dots only. Okay, so that's our domain. Our range, let me go ahead and box our domains from the two problems. So there's our domain. The range on this problem, okay, so let's do this one in green also. Range, well, it's where we have our smallest y coordinate to our biggest. It looks like our smallest y coordinate starts at -1. I'm put a little green dot there to show where my y coordinate begins. And then drawing upward, it looks like it would be at +5 is my biggest one. Okay, and actually let me just underline the 5 there. Okay, so this one is -1, the smallest y coordinate, to 5, the biggest y coordinate. And then that's it. Okay, so there's our range for this graph. Now the second part, part B, is to use the vertical line test. Well, if I draw in, I could draw more than one, but here's a line. All I need is one line to show it, though. As soon as I draw a single vertical line that passes through the graph more than once, it means it's not a function. Okay, so vertical line passes through graph more than one time, that means it's not a function. Okay, because that means that you would have repeated x coordinates. So for instance, where I drew this would be where x is -4, so it happens twice there. X is appearing twice. Okay, so we can't have that repeat. That's the way that functions are defined. Okay, however, this is still a circle. Circles are important for us in math. However, just by definition, it is not a function. Okay, anyway, so that's that. All right, so that's our introduction using domain and range notation and figuring out what makes a function. Okay, so thanks for watching. If you do have questions, let me know, and I'll see you again soon.